Hello, can you hear me? If you can hear me, please send me a message or okay. Okay, thank you. Okay. Welcome to our further learning exercise session 3. In this exercise, you will be familiar with network X and be able to solve it, uh, be able to use it to build a FMI station graph, and also be able to solve the GTV minimization using closed form and be able to solve the GTV minimization using gradient method. Okay. Uh, our first Our first task is to build an empirical graph using the data here. So the data we use today is FMI data 2025. The FMI means Finnish Meteorological Institute. It means weather station. So, for example, this name is one weather station, and this is another weather station, and we need to use all this data to build a graph. So in each node of this graph corresponding to one station in this data set. For example, I draw example here. For example, this graph sorry, this node means this station, and it contains the coordinates and some data. I will explain it later. And for the edges in graph, we choose four nearest neighbors for each node. For example, for this node, we choose four neighbors. For example, 1, 2, 3, 4 here. And for this node, we also choose four nearest neighbors. For example, 1, 2, 3, 4 here. So after this, we have the add edges node here. We have four neighbors, and add these four nearest neighbors to each node. After this, you will build a graph which contains all these stations and its four nearest neighbors as edges. Any questions so far? Okay. And our next task is, next question is how to deal with the data in each node. Briefly speaking, we use the Tmax and the Tmin as our features and the YTmax as our label. You can see from the code here, we combine Tmax and the Tmin use as our X, which also means feature. And here we use Tmax as our label. And after that, we use train test split to split the dataset into train datasets and the validation dataset, also test dataset. And after that, we need to add this train dataset and the validation dataset. And the weights, you can assume that our initial weights are 0. And the coordinate means latitude and longitude for each station. And we need to add this information to our node, which is built here. Any questions so far? Okay. Uh, then our next task, we learned from the last lecture the GTV minimization, which looks like this. And if we use linear regression and MSE loss, which looks like this, then we can solve this GTV minimization using closed form. which is introduced in our Federal Learning Book section 3.4.1. How we do that? First, in each node, the upper index I here means node I. So in each node, we calculate this capital Q using this equation. And the MI here means how many data in each node. In our case, uh, it's always 10, I feel, because in each that data set, we have 10 rows. Oh, sorry, 8, because we also did the train test speed, so it should be 8. In our data set, I feel it's always should be 8. We'll check it in the code. Okay, and for each node, we calculate this capital Q I here and the lowercase q I here. And after that, we stack the after this qi and plus some Laplacian matrix, and also stack the lowercase qi like this. And then the TTV optimization can be right like this equation. It's same as this one. So in this equation, we can solve it using closed form like this, assuming that Q is invertible. Any questions so far? Okay. Then first you need to implement the capital QI and the lowercase qi. Capital QI here, you need to implement according to this equation, and this lowercase qi according to this equation. And after that, you need to stack the capital QI and the lowercase qi in here and here. And after that, you can calculate the optimal W for the GTV minimization using this equation. Any questions so far? Uh, so next, it's not always practical to solve a optimization problem using closed form. In machine learning, most time we use some iteration method, for example, the gradient method. In our book, section 5.3, we introduced algorithm 5.1, which is using the iteration method to solve our GTV minimization. And to do this, first you need to compute the local gradient like this. I can show you the algorithm 5.1 here if you can see. Okay. And first and the updated rule 5.10 is here. So first we need to compute the local gradient, which looks like this, and then compute the graph penalty, which looks like this. So this is local gradient. And this is graph penalty. And then we add them together and use this gradient to update W. So your task is to implement this local gradient and graph penalty and update the rule. Any questions? Well, that's basically all I need to introduce in this assignment. You can ask questions, ask any question about this assignment if it's not clear. Okay. Uh, okay, one question is between closed form and the greeting method, which is frequently used and why? Of course, that gradient method is more frequently used because the reason we can solve it in closed form is the assumption that we use linear regression and MSE loss. It's not always uh, practical. We can we can build some model based on some real data using linear regression. Most time we use some more complex models like neural network or something. In that case, it's not really easy to solve this using closed form. So we need to using gradient-based method. And our next question, can I? Okay, okay, of course. One question is, can I ask something not related to assignment? Okay, of course you can ask. Uh, wait. Okay, first I check. The first question is the deadline for the project. Uh, I'm not sure about the deadline, but of the project, I need to check it after this session. I will reply. Or you can send me a message while Slack, and I can reply to you. And is this project mandatory? Um, and next is uh, suggest me some framework or library about decentralized affair. Okay, these three questions. I suggest you ask them while Slack so I can check the deadline and if it's mandatory and some related topics. I need to check it later. And we have a question that while trying to run the add ages function, getting error with this. Um, like what kind of error? So you have a error in add ages in this one, right? In this k neighbors graph. Yes, this one. But in the first task you will use the add ages function in here. Uh, the add ages function have two parameters. The first is g, which is graph. Uh, we use this one, gfmi no ages as this g here. And for neighbors, you can set it for or just use the default as for. It works. And I need to know what errors you get to answer your question. Oh, okay, I see the arrow. Um, it looks like something wrong with coordinate. Mm, let's see. Sorry, I will check this error later. I now I answer another question. Is their question said that it's okay to create extra cell in notebook. I feel you, of course, you can create extra cells to check your output and something else, but I'm not sure if it will disrupt the checking procedure. Um, my suggestion is you can create your check cell and delete it before submission. And the next question is, can you please explain this code? This deep copy function. Okay. Mm, okay. One question about this deep copy function. Um, this deep copy function here is try to avoid directly modify this graph G here. In this case, it's okay, I feel, if we modify G because this G we passed it to this add edges is our no edges graph. And we need to add edges to this graph anyway. So I feel in this case it's okay to modify this G. And why we do this here is because we want to keep the original version of this no edges graph and uh for backup, I feel. But in next but in next deep copy here, for example, in this gradient method, we use this deep copy here because in this gradient function, we will change the weights in each node. And we want to keep its original width, like the original width we can assume as all the original width is zero. And we only keep this, we only change this copy version of this graph. So we can train it again using our original graph.